In this video, we are going to see how to perform arithmetic operations using NumPy arrays. Let's see some examples. The first thing that we are going to do is create a new NumPy array using the full method. This method will fill an array with the shape that we give it as input, with a value that will also pass to the function. For example, in this case, the array that we want to create will have 3 rows and 3 columns. And we'll fill this array with the value 5. And now we are going to pass this function another parameter that we can specify for all the functions that create NumPy arrays. And the name of this parameter is dType, data type. That is the type of content that the array will hold. Let's give it the data type float32, because we want our values to be represented by floating point numbers of 32 bits of precision. And now we're going to create a new array using the full-like function. And what this function will do is take another array as input and create a new array with the same shape as the array that we pass as input, full with the value that we specify. In this case, we'll create a new array filled with the number 2. And now let's see what these arrays look like. Let's execute the cell. And here they are. The first one is a 3 by 3 array with the value 5 in all of its entries. And the second array has the same shape, but is full with the value 2. And now we're going to do some arithmetic operations with these 2 arrays. The first thing that we are going to do is add these 2 arrays. Let's write full array plus 2 array. And what NumPy will do is iterate over the elements of each of these 2 arrays and add those elements together. For example, it will take the element from the first row and the first column in the first array, and it will add it to the element in the same position from the second array. Then it will take this element here and add it to this one. As you can see, it'll perform a for loop in which it'll take the elements of the arrays and it will add them to create a new array. And that is the magic of NumPy. It hides the complexity of performing these kinds of operations from us. We simply declare what we want to do, and NumPy will do it for us. And by the way, it will perform these operations using routines written in the C programming language, which run much faster than if we did them using Python. Now let's do another operation. How about subtracting these 2 arrays? Let's write first array minus 2 array. And as we expected, 5 minus 2 is 3. So we ended up with an array filled with the value 3. Now let's try to multiply both arrays. Let's write full array times choose array. 5 times 2 equals 10. Look at how all these operations respect the dimensions of the array. Now let's try a division. Let's divide the full array between the choose array. And obviously, 5 divided by 2 is 2.5. Now let's raise the full array matrix to the second power. here it is. Obviously, 5 squared is 25. As you can see, here we used a scalar number instead of a NumPy array. When we do that, NumPy understands that we want to take every element in the array and apply this operation to that element. And it will do it as if we had created an array of the same shape as the full array with this value in every entry. We could also compute the logarithm of an array. This is the natural logarithm of 5. Or we could even do the opposite. We can raise the number e to this array. Another thing that we can do with an array is compute the sum of its elements. And we can do it with the sum function. As we know, the full array has 9 elements, and all of them are 5. So 9 times 5 equals 45. Pretty much every arithmetic operation that is available to scalar numbers is also available to NumPy arrays. And now let's try something different. Let's add the elements in the array, but instead of adding them all together, let's add the elements row-wise. And then we'll try column-wise. To do that, we use the argument axis, where we specify the axis along which we want to apply the operation. Let's call again the sum function and give it axis equals 0. This will give us an array with 3 values, all of which will be 15. Because what we've done is add together the elements of each column individually. That is, the 5 of the first row, the 5 of the second, and the 5 of the third. And we've done the same thing with the rest of the columns. Now, let's do the opposite. Let's do it row-wise. And as we expected, all the values are 15. Now, let's do a more complicated example. This here is the probability density function of the normal distribution, our beloved Gauss bell. Now, thanks to NumPy, we're going to take an array with the values of the x-axis, and we are going to compute the probability density of each of those values. For that, we declare the variable mu equal to 0, and mu will be the mean of the probability density function. We create another variable called std, and we initialize it as 1, because we'll work with the standard normal. And we are going to create the x vector using a new method called linspace. Linspace takes 3 arguments. The first is the minimum value that we'll set to -5. The second argument will be the maximum value, and it'll be equal to 5. And the last argument is the number of elements that we want the array to have. What this will do is take the segment between -5 and +5, and it will chop it into 100 pieces, all of them with the same size. And the position of all those cuts will be each one of the values that we'll store in the X array. And for each of those values, we are going to compute their probability density. And we'll do it with this formula over here. What I want to show you with this is that NumPy allows us to apply mathematical formulas to an entire array in a very natural way, as we would do for a single value. And let's write std which is the sigma value here, times the square root of 2 times the number pi. NumPy also stores some important constants like the number pi, the number e, etc. And this will multiply it by the result of calling the exponential function on the following expression. -1/2 times x minus mu divided by the standard deviation, and all that squared. Okay, we already have our probability density function, and now what we're going to do is visualize this function with a plot. For that, we're going to use the Seaborn library that we imported above. And we are going to pass it the X array that we created before and the probability density function that we just generated. Let's give the plot a title. Standard normal distribution. And here it is. On the x-axis, you can see the values of the vector that we created above. And on the y-axis, you can see the probability density function of the standard normal. As you can see, NumPy allows us to do fairly complex mathematical operations, working at the same time with large amounts of data in a very intuitive way. We've treated this formula as if x was a single value, and NumPy has been able to apply the function to each of the values of x.